Hello, my name is Arnaud Delorme, and this is part 1 on a series of video on independent component analysis applied to electroencephalography time series, so EEG time series. So this part is about what is ICA. And so ICA is an independent component analysis. This is a signal processing method to separate independent source linearly mixed in several sensors. And so, for example, it can be applied to many different types of signals. It can be applied to, for instance, data from microphones. So if you have 5 microphones in a room recording different sounds, like for example here.
How did that happen?
And then you apply ICA to separate these sounds. And based on their statistical independence, you can separate the sound. That's the second sound. Then we have a voice.
Independent component analysis is a new data tool that is sensitive to higher order structure in multidimensional data.
And so all of these sounds were embedded in the original signal right here. And based on the statistical independence, the projection of these sounds on different microphones, ICA was able to separate them. So it's the same principle for EEG, where we have electrodes here instead of microphones. And then here is a representation of the cortex, the skull, and the skin. So if we have a EEG source here, a patch of local synchrony that projects to different electrodes, and then we have another patch here that projects to the same electrodes, it's similar to having different conversation projecting on different microphones. So in this case as well, we can apply ICA. So that's called the cocktail party problem. And so we showed earlier how the projection on different microphones can be separated with ICA, and then similarly the projection of different brain sources on different scalp sensor can be separated with ICA. So how does this work? Well, ICA recovers a version of the original signal. So we have the data. Data is X, that's the data we record, different channels. And ICA is going to find for us W, which is the mixing matrix, and U, which are the original source activity. So the different sounds in the case of source separation with sound source separation, or different brain sources and artifacts in the case of electroencephalography brain data. And while ICA simply decodes the output and finds an orthogonal matrix, ICA attempts to make the output statistically independent while placing no constraints on the matrix W. So we'll see that in a little bit more detail later. But here is an example of 2 sources. So we have source A and source B, and then we have a linear mixture of these sources. So this is 1 times A minus twice B. This is 1.57 times A minus 0.33 times B. So these are the signal from the microphones, or these are the signal from the scalp channel we record, and we want to recover these sources. So we apply ICA, which is going to find the estimated sources and the mixing matrix, and it can recover the source. There is the polarity is lost, but I will go into that into more detail in some of the lecture later. And so ICA is able to recover the source, the original source. So some historical remarks. The first ICA paper was published in 1986 by Ero and Juten. And then in 1995, we had the first Infomax paper by Bernd Sejnowski. Amari and collaborator added the natural gradient to the Infomax algorithm, and we're going to see that next lecture. And there were also other ICA algorithms developed, such as JADE by Jean-François Cardozo in 1996. Application of ICA to biomedical signal. The first application to electroencephalography data was by Scott McCaig and collaborator in 1996, and to fMRI data by Micron and collaborator in 1998. There's many different ICA algorithms. There are confidence on blind source separations, and there's hundreds of ICA algorithms. These are some of the most popular. For instance, you have separation of source based on information theory, that's InfoMax, based on Bayesian probability theory, such as maximum likelihood estimation, negentropy maximization, nonlinear PCA, statistical signal processing, such as JED, which we saw before. So which one is best? Which one works the best? We actually have a paper about applying all these algorithms to electroencephalography data, and we'll go into that in some of the future lecture. But on the theory, at the theory level, there's also been a paper published showing that on idealized data where the sources are truly independent and we have infinite time series, all of these algorithms will be able to recover the source. So there was a first paper in 1996 showing that InfoMax and maximum likelihood estimation were mathematically equivalent. Then another one in 1999 by Lee and collaborator on InfoMax and negentropy, and then another one on nonlinear PCA and InfoMax 1997. So they all work in theory. We'll see how that works in practice in some of the next lectures. So this is to be continued. In the next lecture, we'll talk about how ICA works.